Okay. So for this sample problem, something important just conceptually to think about is when water moves from one area to another area, it's going to also bring mass or weight. Like it's going to bring that water weighs something. For example, here's a scale. Here's a cup of water sitting on that scale. If that cup is, let's say, halfway full, if I add more water to it, right? Now it's more full. That cup is now gonna weigh more on that scale. Um, and so that's super important to understand when we're thinking about this problem. Okay, so this problem says, which of the following solutions will gain the most amount of water? So which is gonna have gain the most water? If placed into a sample of pure water, so the sample is pure water, um, in a piece of dialysis tubing at the temperature indicated. Okay, so let me just draw a quick diagram to show what they're saying. So they're saying, here's a beaker of water. Here is a piece of dialysis tubing, which is essentially like a cell. It mimics a cell membrane. So here's a dialysis tubing or a cell. That cell has pure water in it. So we know that the water potential of that cell is going to be equal to 0. And we're putting it in a solution. So I'm going to use yellow. So we're putting it in a solution of either solution A, B, or C. And we want to know, well, first off, we know that because these have solutes dissolved in it, we know that their water potential in here is going to be negative. It's going to be less than 0 because there is solute. Okay, I'm going to pause it for just a second. So what does that mean? Because we know that will move, water will move from an area of higher water potential to an area of lower water potential. Remember using our number line analogy that 0 in this case is technically greater than anything less than 0. So any of these solutions we know are going to have a negative value. Therefore, we know that the water, regardless, is going to leave the cell. When that water leaves, just like our example up here, this container is now going to weigh more. If I took the cell out, this container will weigh more than it did before I put the cell into it. Okay, so we want to know which of these solutions is going to result in the most water going into the beaker. So, really, what are we trying to find? We're trying to find which of these solutions will have the most negative water potential. Which one is going to have the water potential that is the most negative? Okay. So, why don't you take a second to see if you can draw the two equations? What are the two equations that we'll need to solve this? All right, and so we can see here's our two equations that we'll need. In this case, we're assuming it's an open container. In this open container, how can we assume that? Well, even if it doesn't tell us, we see here that there is no pressure potential given to us. So we're assuming this is equal to 0. So all we're going to need to find is the solute potential using this equation. Why don't you go ahead and set up this equation and see if you can plug in the values for each of these numbers or each of these components of the equation for each solution. As you're doing this, I think one of the important ones to think about is in our solute potential equation is this first letter I, right? So we need to look at the solute. What is the actual solute, and how's that going to help us understand the letter I? So remember that for sugar, any type of sugar, the ionization constant I is going to be equal to 1 because it doesn't dissociate. So here I know that solution A, the I is going to be 1. In solution C, it's another type of sugar, glucose, it's going to be 1. However, in B, solution B, the ionization constant is going to be equal to 2 because sodium, remember that sodium and chloride are going to dissociate into two separate ions when they get dissolved in water. Okay, go ahead and pause again and try to keep solving. Okay. So remember what we were looking for. So here I plugged in the ionization constants for each of them, the molar concentration given here with tonicity, and the pressure constant R is always going to be given to you on the equation sheet, 0.0831, and the temperature given here in Kelvin. Plug that in. You can see again what we were looking for. We were looking for the solution that would have the most water going into it. So we were looking for the water potential that was the most negative. In this case, -49. So it looks like solution A is our answer. That is the solution that will gain the most water. How else could we have solved this without plugging all of this in? Well, we know that each of these, the value for R is going to be the same. So we can pretty much ignore R because it's going to be the same number for each equation. We could then turn our attention to the two numbers here for ionization constant and the molar concentration. I can pretty much rule out choice C because just by looking at it, I know that these two numbers multiplied together are going to be much greater than 1 times 1. Therefore, I'm between A and B as being the most negative answer choice. And now all I have to do is turn my attention to the temperature. And which of these numbers is bigger? Well, 2 times 298 is definitely bigger than 2 times 290. So I could have figured out that it was answer A even without doing any actual calculations in a calculator. Okay, hopefully that was helpful. And thanks again.